Welcome to the first talk of the Computational and Experimental Chemistry Symposium. The symposium is dedicated to bringing together the computational simulation community and experimental researchers to exchange scientific ideas and to learn the current state-of-the-art modeling, analytical, and numerical tools together with advanced experimental techniques. We hope that our attendees, colleagues, and their families are safe in the ongoing COVID-19 pandemic. Today, there will be two lectures presented by Dr. Miguel Jorge from the University of Strathclyde and Professor Carol Morrison from the University of Edinburgh. I'm Dmitry Lepshin, a PhD candidate at the University of Edinburgh and an initiator of this series of lectures. Questions to our speakers from Zoom and YouTube will be moderated by me. Please use both chats to ask questions at any time. I would like to acknowledge technical support provided by the International Adsorption Society and Dr. Dan Siderius in particular. Now I would like to introduce the first speaker, Dr. Miguel Jorge. Dr. Jorge is the lecturer in chemical and process engineering at the University of Strathclyde. His research interests include computational design of new nanoporous materials, developing new models for adsorption in nanoporous materials, and many other fields. Among his contributions, he contributed to the development of the code to analyze interfaces between fluids. He also improved a number of force field models of MOFs and alcohols and other substances. So now, Dr. Jorge, I give a word to you. So I will stop my demonstration and you can start yours.
Okay, thanks, Dimitri. So hopefully everyone can hear me well. I'll start the screen share. Okay. Okay, so welcome everyone to the very first talk. It's a very, very big pleasure to be kicking off this interesting meeting, even though it's virtual. And of course, notice the change in venue. I was expecting to be in Edinburgh now and delivering this talk to a live audience. Instead, I'm welcoming you from my humble abode and speaking to you through virtual means. Well, it's the nature of the times, I guess. The pro, of course, is that I can do the talk in my shorts. So clearly, I'm happy with that. So that's fine. So today, I'm going to tell you about the research we've been doing in my group about trying to develop new models and new approaches to describe, understand, and predict behavior of nanoporous materials. So it's quite a general talk, but as you will see, it's quite it becomes a bit more specific as we go along. So to start, I mean, Dimitri also asked me to make this very in a way explanatory in terms of context and methodology and so on, so we can bridge existing gaps, but potentially. So I start with this diagram, basically explaining the different length scales and associated time scales that can go from all the way from molecules to processes. As a chemical engineer, of course, we're interested in what happens at the process level, but of course, more and more we need to understand what happens at a very low level of molecules and atoms in order to inform our development and improvement of processes. And in the middle, of course, we have materials, which is what this talk is mostly focused on. And of course, at each length scale, we have relevant simulation techniques that we can use. So normally in chemical engineering design, we use process simulators. Here are some examples which are updated now, of course. And this deals with macroscopic large-scale processes. Okay? CFD, computational fluid dynamics, also deals with meso to macroscopic phenomena, mostly related to flow. And the main characteristic of this kind of model is that it mostly describes the medium as a continuum. Okay, so at this high level of scale, it's okay to describe things as a continuum, but as you go further down in length scale, it becomes it no longer becomes a good approximation. So we have to introduce methods that take into account the discrete nature of matter. Okay, and the first kind of method that I've mentioned here is mesoscopic methods like lattice Boltzmann, DPD, etc. Okay, so these are methods that, as I said, take into account the discrete nature of matter, but also represent matter as approximate, so groups of atoms and molecules, etc. Down here, this is where my main training is focused on, which is molecular simulation. Okay, so now what we start to do is we start to represent substances based on their constituent atoms. So the atom is basically the unit that we use to progress our simulation. And then, of course, you can go even further down into the realm of quantum mechanics. And of course, there, the unit is the electron and the proton, and so it's all the subatomic particles. Now, of course, the caveat of all these high levels of theory methods is that they're limited in time and length scale. Okay, so we can't represent a material, for example, using quantum mechanics, and not even using atomistic molecular simulation. So if we want to simulate materials, we have to use essentially mesoscopic methods. But what we want to do is we want to try to keep as much of the underlying physics and chemistry, make it as realistic as possible. Okay, so that's where multiscale modeling comes in. And I know it's a buzzword, but what it essentially means is we have a modeling framework, and there are different flavors of that. And I'll tell you what flavor we are using in our group. But essentially, we try to bridge length scales and incorporate a bunch of different modeling levels into a single framework. Okay, and thus we are able to, like I said, keep the underlying physics and also represent systems at higher levels of length and time scales. So going back to molecular simulation, essentially it's a theoretical method that is based on statistical mechanics. So what we do essentially, so statistical mechanics essentially is a theory that bridges macroscopic properties like thermodynamic properties, temperature, pressure, density, etc., with microscopic behaviors of systems or microstates, okay, which are typically characterized by positions and velocities and orientations of molecules and atoms. Okay, so StatMech essentially allows us to calculate averages over microscopic states and transform those into macroscopic properties that we can relate to real-life experiments. Okay, so essentially that's what we do in a molecular simulation. We create a very large number of microscopic states. We evolve those states over time or over any reaction coordinate, and then we calculate properties by averaging over a very large number of microscopic states. So essentially, it is just like an experiment, except it's an experiment that uses a model for the atomistic interactions. So in reality, we have real molecules interacting through forces between them, intermolecular forces. In the computer, what we do is we assume a given functional form for those interactions, which is called a force field or a molecular model. And then we, as I said, progress these trajectories in time or in a reaction coordinate, and we get macroscopic properties. So we average. So in a way, I like to think of a molecular simulation as a computer experiment using a virtual model. So in application to computational material design, essentially what we want to achieve is we want to have a way of understanding how materials are made and what controls their performance in target applications, so that we can change the properties of the material in a bespoke way to suit particular applications. And so modeling is essential, any sort of modeling is essential to reach this goal, because if we don't have a profound understanding of the theory behind these processes, we can't hope to control them in a meaningful way. So in a way, for the case of materials, I like to split this into two steps. So the first step is we need to understand the relationship between synthesis conditions say composition, temperature, pH, pressure, etc., and what comes out of our experiment in terms of material. Okay, so do I produce a material that's ordered? Do I produce a material with large pores, small pores, a mixture of pores? Is it disordered, etc., etc.? So how can we correlate in a way or relate the synthesis conditions to structure and properties of the material? And then a second stage, and so my talk is actually split in two halves. The first part, I'm going to talk to you about this first challenge, relating synthesis to structure and properties of material. And then the second challenge is, now that we know what the material looks like, can we predict how it performs in the applications of choice that we're interested in? Okay. And the second part of my talk, I'm going to give you an example of how we can do that and improving models to achieve this predictability for the particular case of gas separations in metal organic frameworks. Okay. And as I told you before, we actually need to use multiscale modeling because otherwise we couldn't sample the necessary time and length scales. And it helps us understand the underlying mechanisms of the material synthesis in a way that's hard to do experimentally. So this is the flavor of multiscale strategy that we're using. So essentially, it's a bottom-up modeling strategy. We start with a very high level of theory and run quantum calculations on small molecules and small ensembles of molecules. And we use the results of those calculations to parameterize classical atomistic models. So we go one level up. So this is now classical atomistic simulations, which can represent real molecules. And then we use those results of those simulations, which are necessarily limited in time and length scales, as I explained. We use that to calibrate the parameters of a mesoscale model, which is now able to reach length scales that are more relevant to the case of actual materials. Okay. So it's a chain of models from progressively higher level of theory to lower level of theory, but small length scales to high length scales. And so the idea of this ladder of different levels is very important because we are able to keep the chemical specificity in our model. So if you start straight from a mesoscale model, say, for example, lattice model of surfactant self-assembly, you can tell a lot, you can learn a lot about the physics, but it's hard to say that you're simulating a particular surfactant under a particular set of conditions. Whereas if we adopt this multi-scale bottom-up strategy, we can say, actually, we're simulating this ammonium surfactant with 10 carbon atoms in a chain with salt added at a given concentration and temperature, pH, etc. Okay, so the key idea is that we keep the chemical specificity so we can relate this directly to experimental results. And I'll show you some examples of how we do that. So the first example that I'm going to show in this part of the talk is periodic mesoporous silica. Most of you will be familiar with this kind of material. So the walls are silicon dioxide, SiO2, so the same as zeolite materials, but the walls are amorphous. However, the pores are mesopores, which are relatively wide pores, arranged in a very ordered array. Okay, so we have mesoscale order in the pores, but no microscale order in the walls of the material. And the way they're synthesized is through self-assembly of a surfactant, which forms these cylindrical micelles or other forms of micelle, other types of micelle, as I'll show, but essentially forms a liquid crystal. And then silica condenses around this liquid crystal. So you polymerize the silica, it forms chemical bonds and forms a inorganic scaffold around these micelles. Eventually, what you can then do is you can burn off the surfactant or remove it in some other way, and you're left with hollow pores where the surfactant used to stay. Okay, and a relatively rigid silica scaffold. Okay. So this is the system we're going to probe, and it spans several phenomena like self-assembly, condensation reactions, phase transitions, nucleation, etc. And it's really hard to probe all of those aspects at all the length scales that are needed and time scales that are needed to understand the synthesis process. So that's what we're trying to achieve. So starting from the quantum calculations, we ran some quantum calculations on silicate molecules because at the time there was no atomistic model of silicates that was satisfactory for a wide range of pHs that we wanted to simulate. So we obtained some geometric and electrostatic parameters, point charges, etc., on those silicate molecules. And we use those to parameterize this new model, atomistic classical model of silicates. Okay, so we did this already more than 10 years ago. And we started running some atomistic simulations of the system. So the solution essentially contains water as an aqueous medium. Silicates are added as a silica source, of course, and you've got a surfactant solution. So the surfactant, the typical surfactant is an ammonium surfactant. So it has a cationic, a positively charged head group in purple here, and a long hydrophobic alkane chain, which is apolar in green here. Okay, and of course we need to add counter ions, which in this case are bromide counter ions, to neutralize the charge of the head. Okay, so we use these atomistic force fields, as I said several years ago, to understand a bit more of the early stages of the synthesis of these mesoporous silica. And what we saw was that when you add silica to the system, the surfactant on its own forms a very small spherical micelles, and you can see here. This figure shows the density profile as a function of the distance from the center of the micelle. So on the left here, you have the tails, which are hydrophobic. So they move away from water. They self-assemble at the center of the core of the micelle. And that core is very dry. And then you see water here in blue, starting at the edge of the core. And then the purple peak is the distribution of head groups. So those are marking essentially the boundary of the micelle because they're interacting with water, they're hydrophilic. So it's this hydrophobic balance that determines the size and the shape of the micelles and aggregates that the surfactant is able to form. Okay, and of course, there are several parameters that you can play with in order to tune this. For example, the length of the chain. The longer the chain, the larger the micelles will be, and eventually you can change the curvature. But you can also play around with the interactions between the head groups. So the head groups are positively charged, so they're repelled by each other. Okay, so if you have a salt like bromide that absorbs here on the outside of the micelle heads, then that diffuse layer kind of screens the interaction between the heads, but not very effectively. So they're still very repelled, which means that the micelle has a very high curvature, which essentially translates into very small micelles. Now, when you, instead of bromide, when you have silicates, the silica actually absorbs on the inside of the head group of the micelle. And that completely changes the balance of interaction. So now the silica is able to screen the repulsion much more effectively and lead to much larger micelles than before. Okay, that's because the surfactant heads are now able to approach each other without feeling that extreme repulsion that we felt before. Okay, so this is the first evidence from our modeling that silica actually increases the micelle size of the surfactants. But of course, we were limited in that we couldn't simulate larger systems. So, you know, we asked, what does that imply in terms of the synthesis of material? And so we went the next step up and we coarse-grained the model. So this is essentially a way of representing a group of atoms as a single interaction center. Okay, so instead of having, for example, here, I don't know, about 30 interaction centers, one for each atom, we have here a coarse-grained model of that surfactant with only 5 interaction centers. Okay, and water, for example, you lump together 4 molecules into a site, and the silicate is also a single site. Okay, so it's simplifying the model quite a lot, which means that, of course, you pay a price in terms of precision and accuracy of your representation of reality. Okay, so the key is, how do you map the results of the atomistic model into the coarse-grained, more approximate level of theory? Okay, and of course, the way you can't map everything, so because you necessarily need to lose information on going for a lower level of theory. So the key is actually trying to find the properties that you actually need to map to make sure that you retain that level of accuracy when going up one step. Okay, in this case, we mostly focused on structural properties of the micelles. Okay, because that's what we want to understand, is how these micelles interact and develop. So here I show you the same kind of density profile, but now I have the atomistic in full lines and the coarse-grained in dashed lines. Okay, and we adjusted the parameters of the coarse-grained model so that we actually replicate as best as possible the distribution of the atomistic model. Okay, so that's our model tuning step. And then we can validate the model later. So for example, we showed using the pure coarse grain model that the pure surfactant in water was able to reproduce the qualitatively and very closely quantitatively the experimental phase diagram of the surfactant. So at low concentration, you have small micelles. If you increase the concentration, they start to be forming these worm-like micelles, so much longer. And in fact, you see a shift here. This boundary is actually measurable experimentally. And then at even higher concentrations, you start to see these hexagonal liquid crystals, like hexagonal arrangement of cylinders, and then eventually a lamellar phase at much higher concentrations. Okay, so our model is able to describe this qualitatively. Now, the big question is what happens when you add silica? That's completely new. I mean, people have understood these pure surfactant phase diagrams, okay? So the key to understand first is that the synthesis of the silica materials takes place at very low concentration. So in the regime where you would see surfactant small micelles on their own, okay? So how do you go from this to something like that without changing the concentration of the surfactant? Okay, essentially that's what you do in the material synthesis. So we added silica to an equilibrated micellar solution. So in this case, just silica monomers, which have a negative charge because it's high pH. Okay, so these are deprotonated silicates. And as I showed you, they interact very strongly with the micelles. They cause the micelle size to increase. And in our mesoscale model, we could simulate for long enough to see that actually the equilibrium system is a worm-like micelle. Okay, at very low concentration. So you wouldn't expect to see this in a pure surfactant solution, but with silica, you have a sphere to rod transition. So this is a very important step in the synthesis of these materials. So we went further and we asked, okay, can we actually replicate an actual hexagonal liquid crystal using this model? So we took a study from Brad Schmelke's group from the late 90s, where they saw, under very carefully controlled conditions, they saw the formation of these hexagonal liquid crystals. So we tried to replicate, so they did some NMR experiments to find out what the silicate speciation was in solution. So there's a very detailed set of information that we could find in the literature. So we used exactly the same conditions as they had, and we ran our simulation, okay? And to our surprise, well, you know, partial surprise, we weren't expecting this to be so successful. We actually found the hexagonal liquid crystal. So the system phase separated into a dilute phase and the concentrated surfactant silica phase, which had a hexagonal ordering of cylindrical micelles. Okay, so just like what was seen experimentally. Okay, so this is kind of quantitative post facto validation of our model because it reproduces what experiments see. So now we went back and we thought, okay, can we understand a bit more about how this works and what's the mechanism behind that? So this step you already know. So if you start from a solution of surfactants, it self-assembles into spherical micelles. I showed you this before. You add monomers, it forms worm-like micelles. However, we know from experiment that silica is not present in monomeric form, except at the very start of the synthesis, because soon after you add silica to water solution, it starts to polymerize. Okay, so we thought, okay, why don't we add some dimers, which are the next stage in polymerization? So we have now pairs of silicates bonded together by chemical bonds, and so if we add dimers, we already see this formation of hexagonal liquid crystal. But we never see that if we only have monomers. Okay. The other interesting case information is that this is actually an equilibrium system, because if we can do that in the simulation, just remove the dimers, replace them with monomers, we go back to a worm-like micelle, and vice versa. If we replace the monomers with dimers, we recover the hexagonal liquid crystal. Okay. So dimers seem to be needed to form this hexagonal phase. Okay. So actually, now we can go back to the atomistic simulations and have a look at what happens when the dimers are interacting with the micelle. And what we saw was that when a silica is in dimeric form, it has two charges, one per silicon atom. And so this allows the silica to bond to two different micelles at the same time, whereas a monomer can only really bond to one micelle. Okay? So effectively, these silicates are acting as bridges between micelles and are promoting the aggregation of micelles together. And that's what actually stimulates the phase separation into that hexagonal liquid crystal. Okay, so then we can play around with the model a bit more and say, okay, how does silica condensation affect the mesostructure? So we start with a system with only dimers, and we can progressively increase the degree of silica condensation. Instead of having 4 dimers, we can have two pentamers. I'm missing the word. 2 formers, right? And then we can have an octamer here. Tetramers, that's what I meant. Okay, so 2 tetramers or an octamer. So essentially, we're keeping the amount of charge in the system, but we're increasing the charge density by making the silicates more closely packed together by chemical reactions. And we can see that we go from a hexagonal liquid crystal to a lamellar phase through an intermediate phase here with the tetramers. Okay. So the degree of silica condensation can control the mesophase structure. And we can do the same, but now instead of changing the degree of condensation, we change the degree of deprotonation. So essentially, we're replicating what would happen if we were able to tune the pH of the synthesis. So we start with half the silicates being charged, so charge of total -4 on an octamer, to -6, and eventually to -8 on a fully charged cubic octamer. And as we see the same transition, okay? So we go from a hexagonal liquid crystal through an intermediate stage to the lamellar phase. Okay, so again, charge density seems to be the key in determining the shape of the mesostructure. Okay, we can also play around with adding co-surfactants. So if we add benzene, for example, it's hydrophobic, so it acts as a co-surfactant. It swells the region of the tails and shifts the balance to a lamellar phase. Okay, that was also seen experimentally by Brad Schmelke's group. They actually added benzene and showed this transition. Okay, and we can revert back by removing benzene. Okay, so this also reproduces experiment, and we were able to span or scan the parameter space of the model, and we were able to find a series of mesoporous silica materials which are found experimentally at roughly the correct conditions, set of conditions. So MCM41 is the one that I was mostly speaking about, with a hexagonal arrangement of cylinders, but we can have a bicontinuous MCM48 phase here and a lamellar MCM50 phase at very high silicon surfactant concentration. Okay. So we then actually went, so that's the first example, is understanding the synthesis of this very old, in a way, it was discovered in the early 90s, mesoporous silica materials. But now more recent work is applying the same approach to understand bio-inspired silica. So the idea with bio-inspired is that we try to understand how nature does this process of biosilicification, where it produces these very intricate, beautiful, hierarchically porous structures, such as in diatoms and sponges, using ambient conditions, dilute aqueous solutions, neutral pH, etc., all of these being environmentally friendly conditions, which are completely different from the conditions under which the typical silica materials are synthesized, which are very high temperature, very high or very low pH, and using harsh chemicals like the surfactants I mentioned. Okay. So I worked together with an experimental colleague trying to understand this bio-inspired silica synthesis, and we started off with a simple system which had been discovered in the mid-90s by Tanev and Pinavaya called HMS. Okay. We also looked at another system that they used, but I'm not going to talk about that in detail. So the idea here is they found some similar materials with hexagonal arrangements, but they argued that their systems were synthesized without any charge. Okay, so these surfactants are now amine surfactants, which are neutral, according to their theory, and they're surrounded by silica, which is also neutral, according to their postulated mechanism. So this is called the neutral templated mechanism. It's been accepted by the material science community for decades. Okay. So we try to understand exactly how these materials are formed using our model. So we did the same kind of coarse graining, but now using amine surfactants. And the key now is that the amine surfactants are pH responsive. So we can protonate them or deprotonate them according to the pH of the medium. Okay. So the first thing I asked my experimental colleagues was, can you determine the pH of the synthesis? Because it wasn't actually reported in any of the previous studies in literature. So it turns out that the reaction mixture is at a pH of roughly 9.2 to 9.5, and the pKa of the amine surfactant is around 10, which means that actually the vast majority of amines are protonated in the corresponding experimental synthesis. So not neutral at all. There's only a small percentage of neutral amines. And also 25% at least of silicates are anionic. Okay, so there's a lot of charge in the solution, which wasn't expected just from the description of the experiment. And we showed that also with titration and also with NMR experiments. So if we now use this experimentally determined pH and the pKa of the surfactant, we can determine the exact speciation of our solution. So we ran that, which I call the charge system, with the charge according to the pH measurements. And without silica, we see formation of very small spherical-like micelles, as we saw with the ammonium. And then it's kind of the same process. We add silica, and that promotes a formation, sphere-to-rod transition, formation of long worm-like micelles. And is eventually, as you add more silica and it condenses further, you form a roughly hexagonal arrangement of cylinders. Okay, this is hard to see, but the green is the neutral silica, and the blue is the surfactant near cylindrical micelles packed together. Okay. On the other hand, if we run the hypothetical neutral templating mechanism where nothing has a charge, really nothing happens. The surfactant phase separates into a blob, which is completely structureless. Okay, and the silica remains in solution. Okay, so there's no incentive for the silica to interact with the surfactant significantly and to promote order in these materials. So we saw essentially that this neutral system was not, this neutral mechanism was really not viable at the experimental conditions. So this sums up what we saw in terms of the mesoporous silica. So at high pH with ammonium surfactants, you have this step going from micelles to spheres to rods, and then aggregation through intermediation of silica, forming this hexagonal mesophase. With the bio-inspired silica, or the amine templated silica, it's much lower pH, but not necessarily neutral. And you see a lot more neutral silica in green here, but you still see the anionic silica bridging together the whole system and contributing to this onset of aggregation. Now, the key here is that the materials are much less ordered than the MCM type materials that were synthesized industrially. Okay, so the key now is trying to understand how we can make something like this, but at much milder conditions. Okay, and that's the next challenge in our modeling experimental work. Okay, so that concludes the first part of my talk. So relating synthesis, using models to relate synthesis to structure and properties of the material. And the second part is now understanding how we can predict performance of these materials using molecular models. So the example now is totally different. It's not on silica, it's on metal organic frameworks, as I mentioned. In particular, we've been working on a very specific subset of MOFs, which are MOFs with unsaturated metal sites. Okay, so MOF is basically a crystalline framework like a zeolite, except it has a metal node. So these are metal nodes, in this case copper dimers, which are bridged by organic linkers. So it's a hybrid organic and inorganic material, which forms a crystalline framework. And these are the pores. So you can have small and large pores coexisting in the same material. Now, in some materials, so these bonds here, these are coordination type bonds. So these are essentially metal organic coordination bonds. And these red oxygens here are from the organic linker, but these blue ones are essentially from solvent, could be water or DMS or something like that. Okay. So when the material is synthesized in solution, you're left over with some solvent coordinating to the metal, but you can actually remove that solvent by heating under vacuum. Okay. So if you do that, you're left with a vacant site, a vacant coordination site. So this is what we call a coordinatively unsaturated metal site, or open metal site also in the literature. Now, as you can imagine, these can have very interesting applications in absorbing particular gases over others, so in changing the selectivity of the material for particular gas separations. That's what we're trying to exploit. Now, the problem with that is that if you want to understand this and predict this from a modeling point of view, if you use just standard atomistic models from the literature, you won't be able to do it. And the reason is those models typically describe Lennard-Jones interactions, dispersion and repulsion, Van der Waals interactions also called, between different atoms, and they can also describe permanent electrostatics between polar molecules and polar atoms. Okay? But what they can't describe is coordination bonds. Okay, they're not designed to describe that kind of chemistry, because it's kind of it's really at the borderline between what we would call chemisorption and physisorption. So you can see it as kind of a weak chemisorption, which is reversible. So models can't do that. So what we need to do is actually going back to the multiscale approach, which I'll show you in a second. So our baseline is our classical atomistic models, which are taken from the literature here for our molecules. So we're looking at separations between olefins or alkanes, ethane, propane, and paraffins or alkenes, ethylene and propylene. It was the other way around. So paraffins are alkanes and olefins are alkenes. Okay, and we're using, again, standard models for the framework from the literature. And the way we run the simulations is using grand canonical Monte Carlo methods. So Monte Carlo is based on random numbers. So you, instead of, in the previous simulations, it was using molecular dynamics, which you propagate the trajectory in time, but now we use random numbers. And the reason we do that is because we want to determine the amount adsorbed inside the material, which means that you need to change the number of molecules on the fly during the simulation. Okay, and we can't do that with dynamics without having significant boundary effects complicating the matter. Okay, so essentially what we do is we artificially couple our simulation box where the material is contained to an infinite reservoir of energy and molecules. Okay, so by exchanging energy with the reservoir, we can keep the temperature constant, and by exchanging molecules, we can keep the chemical potential constant, which is related to the bulk pressure, but actually change the number of molecules or the amount adsorbed in the material as a function of the chemical potential. Okay, so that's the nutshell of a grand canonical Monte Carlo simulation. So if we use just the standard models as they are, okay, just with the van der Waals interactions, you can see that for the paraffins, the alkanes, isobutane and propane in this case, the model works fairly well. Okay, so we have the experiments. These are adsorption isotherms, so it gives you adsorbed amount as a function of pressure at constant temperature. So each curve is a temperature. And we see the dots are experimental data and the lines are simulations. And you see that for these two cases, the agreement is fairly good. However, for the case of the olefin, the model fails completely. So it significantly underestimates the amount of adsorption in the material. Okay. So you might wonder, why is this happening? And of course, that's because the metal is undercoordinated, and the olefins have a double bond, so a double bond between carbon and carbon, which has unsaturated electrons that are lying around, able to be donated to the metal. Okay, so it's this electron donation between the double bond and the metal that forms the coordination between the olefin and the in this case, the copper metal. Okay, now this is well-known chemistry, but of course you can't represent it at a classical level using standard models, okay, because they're not prepared to cope with that electron donation. So what we have to do is, and of course that leads, I should say, to an underestimation, because we're not predicting the chemical or quasi-chemical bonding between the olefin and the metal. So what we actually need to do is use, again, multi-scale approach, where we now use quantum mechanics to obtain adsorption energies on the metal and use those to parameterize new classical models that we can use in our grand canonical simulation. Okay. So without going through too much through the technical details, what we do is we cut out a cluster of the MOF, or we can use the full MOF. We've used both, and you get the same results. And you adsorb a metal using quantum chemical density functional theory. Okay. So we adsorb the sort of model. It optimizes at a given distance to the metal and with a given energy. Okay. And then what we can do is we can move the molecule in steps, either closer to the metal or further away, and obtain what we call a potential energy scan of the system using quantum mechanical calculations. So if we do that, we see here the black points are the data from the DFT, the quantum mechanical DFT, and the purple line is the Lennard-Jones potential, which is a standard model, which has actually been adjusted to match the adsorption isotherm. Okay, so you match the adsorption isotherm fairly well, but you get the mechanism of adsorption totally wrong, because you don't get this very close adsorption of the metal and this very high adsorption energy in the vicinity over 20 kilojoule per mole. Okay, the Lennard-Jones potential replicates neither of those, and it makes up for that missing energy elsewhere in the MOF, which is completely unphysical. So all we do is now we do some energy decomposition to extract the contribution that's due only to the coordination bond. So we exclude repulsion and dispersion and all the other contributions to the energy. What we're left with, we then fit to a classical functional form, which is a modified Morse potential with a power law. Okay, so this is an empirical fit to the FT data. Okay, and if we fit that, we can now add a new site to our model. So this is a molecule of propylene, and this is the double bond. So we now add a site at the center of the double bond that's able to interact directly with the metal. Okay, so that's the only thing we changed about the model. All the rest stays the same because it was doing a really good job at the van der Waals interactions, which we saw before. We don't want to screw that up, but we want to make sure that we also capture the coordination bond. Okay, this additional site only interacts with the metal, and it interacts with the metal through the potential that we just parameterized from quantum mechanics. Okay, and we're using we've modified the standard music code, which is an open source code for grand canonical simulations of adsorption. We've modified that to include this new potential that we parameterized. So we can show that this is now a potential energy map, a cross section over the MOF. We can see that by adding this, we create these energy wells near the coordination side of the metal, but no real change elsewhere in the framework. So we're only changing the environment of the coordination bond and nothing else. And of course, now we can go on to make isotherm predictions. As you can see from that graph, we can compare the old model. This is for ethylene adsorption. With the new model. So the old model was missing this energy well here at the coordination site. The new model has that. And so not only does it predict the adsorption isotherms very nicely, it also gets the correct adsorption mechanism. Now I should say that we fitted the potential to quantum mechanical calculations, but there were no adjustable parameters when comparing to experiment. So these simulations are pure predictions based on the quantum mechanical plus atomistic force field. Okay. So we also showed that we can transfer the same parameters to different olefins. So we parameterize it for ethylene, and that gives you good predictions. But now we can take the exact same parameters, pop it on propylene, and we can also reproduce experimental data. So this is actually, there's a lot more experimental data, which was a richer system. And on 4 different samples of this particular MOF, we can predict the adsorption very, very closely. Okay, so we can transfer from gas molecule to gas molecule. Now, another question we answered is, now can we take the same gas molecule and pop it on a different MOF with the same metal? Okay, so or the same metal unit, that copper dimer paddle wheel. And the answer is yes. Generally, we can do that. So we compared the HCUST1, which was the MOF I showed you before, and now we transfer that to PCN16 and several other copper-containing MOFs. And we got really good agreement with experiments. So this is the dashed lines are again the old model, and the full lines are the new model against the experimental data. So even though agreement is not absolutely perfect, it is really quite good considering the error margins in the experimental data and in the model parameterization. Okay, so the model is also transferable to different MOFs. Okay. Moreover, we extended the model. So before we were dealing with non-polar alkanes and alkenes. Okay. Now we can also deal with polar molecules. So my student, Chris Campbell, that was the main focus of his thesis, was to actually extend this to polar molecules. And we used a test case of carbon monoxide on the same copper paddle wheel MOF. And now, of course, the DFT, the quantum mechanics, tells us that the CO molecules adsorbing upright on the copper with the carbon closest to the copper. Okay, and if you actually simulate this with the classical standard model, you get the opposite. The oxygen is more closely attracted to the copper. Okay, and it's actually, again, much less attracted. So the actual molecule is much further away at the optimal position. Okay, so again, we get the wrong mechanism using the standard models. But if we now use the new model, we get the correct adsorption mechanism. So again, the carbon is here now interacting with the metal in an upright manner. And relative to the standard model, which grossly underestimates adsorption, our new model yields much better predictions of the adsorption in this system. Okay, and we're now extending it further. We're looking at applying it to water adsorption, carbon dioxide, etc., all of which interact specifically with these open metal sites. Okay. So I'm nearly finished. I just want to go over a few conclusions. So the first part of the talk, I showed you how we can use multi-scale modeling to access relevant time and length scales in porous material synthesis, while importantly keeping the degree of chemical specificity of quantum and atomistic models. Okay, and we showed that the material synthesis, we showed some insight into the material synthesis, which progresses by a cooperative templating mechanism whereby silica and surfactant interact together to determine the nature of the mesophase that is formed. Okay, it's not the surfactant on its own that's doing it, and it's not the silica on its own that's doing it. It's a cooperation between the two. And really everything is about charge. So how these charge interactions and charge densities, how we can play with that to change the degree of order and the structure that arises in the material. Okay. And now the challenges going forward are to actually understand how we can develop bio-inspired approaches to material synthesis using these modeling approaches. Okay. So in the MOF predictions, I also showed you that we can use multi-scale modeling to improve predictions of performance of materials, in this case, crystalline MOF materials in gas separation applications. But we again have to use quantum mechanics to get the correct adsorption mechanism because it's based on a coordination bond. Okay, and typical models will not do it even if you adjust their parameters. And this is a very key point. A lot of people in the literature, I've seen a lot of studies where people actually just tweak the values of the Lennard-Jones parameters or the point charges of the model to match the adsorption isotherm. But even if you do that, you get the wrong adsorption mechanism. So there's no guarantee that if you change the conditions, the predictions will still be valid. Whereas we believe our approach, because it's bottom up and it's chemically grounded, will give good predictions in different conditions. So the interesting thing about our particular approach, now other people are doing this kind of quantum mechanics based force fields, but by and large, they parameterize the whole thing from scratch, which is interesting, but has its complications. What we're doing is we're combining existing models for the typical standard part of the force field, the electrostatics and the van der Waals, and we're combining it with a bespoke model only for the specific interactions that we're interested in. Okay, so that means that the model is much more transferable than pure quantum mechanically derived force fields. And we showed that by transferring it to different gases and to different MOFs. And it's also generally applicable to both polar and non-polar adsorbents. Okay? And so improvements in the classical model will all lead to improvements in this approach. So I'll finish off by thanking all my collaborators in MCM41 synthesis. This involves a large team, including José Gomes at Aveiro and Peter Mons and Scott Auerbach at UMass. The bio-inspired silica was done in collaboration with Siddharth Patwardhan at Sheffield, and the MOF adsorption again with Michael Fischer at Bremen and José at Aveiro. And finally, thank you very much for listening, and I'll be happy to answer any questions. Thank you.
Thank you, Miguel. We have several questions in Zoom and in YouTube, so I will read these questions to you.
Okay, go ahead.
So, a question from Lev Sarkisov. What would be the approaches in developing quantum force fields for nitrogen?
Okay, for nitrogen, that's interesting. So we've actually already done that to some extent. We've developed one of these quantum mechanically derived force fields for the coordination bond between nitrogen and copper. Now it turns out that according to our calculations, the strength of the coordination bond is very weak, and so at room temperature or in industrially relevant conditions, essentially the coordination is irrelevant. You can get really good agreement with using a standard force field without the open metal site interaction. Now the whole thing changes when you go to cryogenic temperatures, where the interaction becomes stronger in relative terms with respect to thermal fluctuations, and so there the picture might change. Now, unfortunately, we weren't able to find yet sufficiently detailed experimental measurements at low pressure at cryogenic conditions of nitrogen, so where we can test our model rigorously. So we're looking at that in the future, but for the time being at room temperature, we really can't tell the difference between a standard model and the new approach.
All right. A question from YouTube. It's more like a comment, but I will read it as well. So a comment from Santa Paula's. Silica effect that induces the transition from sphere to rod looks like salt effects.
Yes, it's very similar, because silica, when you pop it in solution, at least in monomeric form, it behaves very much like a salt. It's an ion diluted in solution. Okay, so it's an ionic effect, definitely. It is actually similar. If you use just normal salt, you actually need to go to very high concentrations of salt to promote the sphere to rod transitions. With silica, you need very low concentrations of silica. It behaves a little bit like experiments I've seen on salicylate ions, so larger ions that actually have a hydrophobic region that absorbs closer to the micelle head group region. And if you do that, then you shift the curvature even at low concentrations. So in a way, it's akin to these more hydrophobic salts rather than the typical NaCl kind of salt effects. But it is, essentially, it is a salt effect.
Excellent. Another question from Joe Menon from YouTube. With the HMS and MCM formation simulations, how did you simulate the silica polymerization processes? Did you manually swap out 2 monomers for a dimer, or do some kind of hybrid MD-MC simulations?
It's the former, essentially. I probably should have spent a little bit more time explaining that. So at the moment, our multiscale model is not reactive. So when you run the simulation, the silica stays in the same way as it started. So when we simulate a solution of dimers, we pre-select the number of dimers that we want to put in our system. Okay, so, or in other words, like you said, you replace a couple of monomers by a dimer and you progress the simulation. Okay, now we've already been experimenting with alternating reactive Monte Carlo simulations with non-reactive MD simulations, and we, at least for the beginning, we don't see a big difference between that approach and what we are doing. But then that approach essentially jams because of translation issues between the two methods. So we're now working on developing a new reactive model, a reactive force field that can be incorporated at the same time as the MD in order to develop the self-assembly under reactive conditions. Now, for the silica systems that I showed, it has been shown experimentally that and through modeling as well, that the synthesis progresses in essentially 2 stages. The first is the self-assembly, and the second stage is long-term condensation and polymerization of silica. So even though you have small-scale polymerization at the start to form oligomers, you don't have large-scale formation of a scaffold until you progress the reaction into sufficiently long times. Okay, so we're essentially under that assumption, and that's what the model is showing. If we want to lift that, we need to be able to simulate reaction and self-assembly at the same time. So there are some systems for which the time scales are actually comparable in the sense that we would have to do a reactive simulation. So that's what we're looking at next.
All right. So question from Sebastian Amaya. Can you use kinetic Monte Carlo to simulate the same systems, which would be more accurate?
Okay, another very interesting question. So yes and no. So people have done kinetic Monte Carlo simulations of silica reactions. So the idea there is that you obtain a series of reaction parameters like kinetic factors and activation energies from quantum chemistry. And then you plug them into a Monte Carlo algorithm, which reacts that randomly and progresses the reaction according to those parameters. Okay. Now, what's the main problem with that is is multiplicity of molecules. So silica has 4 possible reaction points, And once you start reacting and polymerizing the silica, the number of possible molecules or distinct species that can be found increases factorially, okay, with a factor of 4, right? And so you very quickly run out of memory just in the ability of mapping out the number of species and the number of possible reactions. That's one problem, practical problem in running the kinetic Monte Carlo simulations, but also in parameterizing them, you know, you would have to then calculate the quantum chemistry, chemical reaction between a 12-mer and all possible pentamers of silica in order to get those parameters, okay? Now, of course, you can do approximations, but then, you know, the model becomes less accurate. So I think the furthest I've seen in literature is formation of octamers of silica or hexamers or octamers of silica using kinetic Monte Carlo. If you want to actually simulate much more extended structures like we do to form material, you can't use kinetic Monte Carlo.
All right. Another question, again from Sebastian Amaya. Other rotations of the adsorbed molecules are incorporated in the adsorption model.
The rotations. Okay, so in the examples that I showed, I think so for the olefins, the rotation will be this way. So the olefin is absorbing perpendicular to the metal axis, okay? So because the interaction center is at the center of the double bond, the rotations are implicitly accounted for by the standard model, okay? So there's nothing changing. You just have a pivot there, and that absorbs the molecule. In the CO, it's a bit different because it's absorbing like this, and so you have a difference whether the molecule is this way or that way, okay? So whether it's absorbing C first or O first. Now, the way, so we actually simulated at the quantum level all these different orientations and determined all the different energies, and that's how we showed that it was much more favorable this way, with the carbon towards the metal. But also, we showed that we can replicate the energies by putting the site on the carbon atom and no site on the oxygen, okay? So when the molecule feels that very strong adsorption, it orients itself with the carbon pointing to the metal. And we actually then validated that, that assumption by looking at the distribution of orientations in the simulation, in the grand canonical simulation, and we saw that indeed the molecules were always oriented in the same way, pointing to the metal when they were adsorbing on the metal. So of course, just to add something else, which if you now have even more complex molecules like CO2, which can tilt, okay, now that becomes a bit of a problem. And we haven't actually extended our model to CO2 just yet, precisely because we need to actually cope with that orientational degree of freedom. And finding out the best way to deal with that is still open.
Okay, excellent. Another question from Joe Menin. So I will read it as it's written. Is it possible to transfer the new MOS functional without further DFT simulations? So is it somehow related to MOS functions, probably?
Okay, so we can do it. We've already shown that we can do it as long as the chemistry is exactly the same. So if we have an olefin double bond interacting with a copper metal, then yes, we can take the same parameters to other olefins and to other copper MOFs. Now, if you change the metal, it becomes, for example, an iron metal instead of a copper, then you have to do a new quantum calculation. We haven't done enough. We've been playing around with other metals now, but we haven't done enough to show or to find out if there's a trend that we can use, okay? So if there's a trend in adsorption energy and steepness of that well that I showed you, if we can find a heuristic relationship between that, for example, and the nature of the metal, then we could potentially predict, using some simple heuristics, predict what the adsorption profile would be by changing the metal. Okay, but we haven't done that in order to answer that question, but it's an interesting one to ask. In terms of transferring to different gases, for example, water or CO or CO2, I think there's no hope except doing a full-blown DFT calculation. Okay, now having said that, the nature of our model, the combination between classical and quantum that we use, means that we only really need to calculate one single energy profile on a new MOF instead of for the pure quantum mechanically derived force fields, we need to map the whole energy grid on the entirety of the MOF, which is much more computationally intensive.
Okay, thank you. Another question from Abhishek Sharma. Again, it's related to MOS. What advantage does modified MOS potential give over Lennard-Jones?
Okay, so the first thing is that the Lennard-Jones functional form cannot capture the nature of that well. Okay, so let me see if I can show you the plot. It's easier this way. Okay, so sorry. So this plot here, right? The red line is the one that we fit with the Morse. Okay, and if we use a Lennard-Jones and we try to fit this, we can get the minimum right, and then we can't get the repulsive region or the tail off into the attractive region right. The curvature is going to be different. Or if we get this tail correctly, we can't get the minimum energy right. So we can't predict, or we can't fit the energy profile as accurately with a Lennard-Jones. We just use the Morse for convenience, I should say. There's no reason to anticipate that other functional forms which are more flexible, for example, a Mi potential, might be able to do a better job. We haven't tried that. We used Morse and it worked, and that's all that matters for us, I think.
All right, and it seems we have another question. So Carlos from Zoom asks if you could elaborate a little bit more on GCMC simulation concept. I have never worked with this technique.
Yes, of course. So I wonder how much time I have to elaborate on this, because this could be a lecture. I give a lecture about GCMC to my students, which is about an hour, but I'll try to keep it short, right? So the idea is that, so if you're familiar with the typical Monte Carlo method, so the typical Monte Carlo is in the NVT ensemble or canonical ensemble, where we fix the number of molecules, the volume, and the temperature, okay? So the way you progress the simulation is you allow molecules to move randomly. So you pick a molecule at random, you displace it to a different place, okay? And then you accept or reject that trial depending on the relative energy between the two. And you plug that into something called the Boltzmann factor. So I don't have time to go into the statistical mechanics of this, but essentially it's a weighted expression of the energy that allows you to say whether you should accept or reject that to minimize the free energy of the system. So by accepting or rejecting those trials, you move to equilibrium. Okay. Now the grand canonical Monte Carlo has a big difference, which is that now you don't fix the number of molecules, you can change the number of molecules, which means that apart from translating and moving and rotating the molecules as you do in normal Monte Carlo, you also need to create and remove molecules. Okay. And again, you need to derive those acceptance criteria based on the Boltzmann factor, but now for increasing or decreasing the number of molecules by 1. So of course, now you can get terms there that depend on the chemical potential, which is the variable that you now fix. So you say, at this particular chemical potential, which is in equilibrium with a bulk gas phase, at equilibrium, I'll have n number of molecules. So you fluctuate n until you actually can average the correct amount absorbed at those conditions. Okay. In a nutshell, that's how it works.
All right. Thank you, Miguel. We don't have questions anymore. So if you can stop your demonstration.
Mm-hmm. Yeah. Thank you, everyone.